Greetings Math 347 fans. This is the second part of a video examining first order differential equations which are classified as autonomous. In our last video we saw a motivating problem. We had a look at qualitative analysis applied to that motivating problem. We more clearly defined what we mean by qualitative analysis and went through qualitative analysis for one final example. In this particular video, we look at an analytic criterion for stability and also at a new concept called bifurcations. So here's the analytic criterion for stability. First, make the observation that if you have an equilibrium solution of an autonomous differential equation, the arrows nearby that equilibrium solution tell us stable or unstable. So if the arrows nearby x star, I'm calling the equilibrium solution, point toward it, x star is stable or asymptotically stable. Again, we're just calling that stable. And if the arrows point away from it, we call that equilibrium solution unstable. Okay, so you can see that actually the sign, the SIGN of the derivative of f with respect to x here tells us whether a solution is stable or not. So in particular, if f is decreasing through an equilibrium solution, we can see it's stable. And if it's increasing through an equilibrium solution, we can see it's unstable. Oops, sorry about that. Now, that information about the stability of the equilibrium as it relates to the derivative of f with respect to x is summarized here. And I want to point out again, so far in this class, prime has always meant a derivative with respect to time. Here, it means a derivative with respect to x. Again, our phase diagram treats x like an independent variable. Now, of course, if f prime is at an equilibrium solution is equal to 0, we can't make a conclusion. A couple of examples of zero slope at an equilibrium solution where the equilibrium solution might be stable or unstable, and then similarly a couple more examples of an f whose derivative at the equilibrium solution is 0, where the equilibrium solution is categorized as unstable. Here, semi-stable, but again, we're just going to call that unstable. So, in summary, the analytic criterion is, given an equilibrium solution x equals x star, if f prime of x star is negative, then x equals x star is stable. If f prime of x star is positive, x equals x star is unstable. And if f prime of x star is 0, then we don't know. The equilibrium solution could be stable or it could be unstable. Okay, once again here, prime on f indicates a derivative with respect to x, not with respect to t. So just keep that in mind. Okay, as an example, let's go ahead and apply our stability criterion to a problem for which we already know the stability of the equilibrium. So here is our logistic growth model, x prime equals rx times quantity 1 minus x over k. So the first thing we'll do is identify equilibrium solutions. That's quick to do. Again, we know that the equilibrium solutions are 0 and k. The second thing to do is to evaluate f prime at those solutions. So if f of x is equal to the quadratic in x, f prime is some linear function in x. Once again, can't emphasize this enough. In this analytic criterion, the stability criterion, f prime indicates a derivative with respect to x, not with respect to t. So if we take that linear function and plug in 0, we get r, which is a positive value, indicating that 0 is unstable. And if we plug in k, we get negative r, which is, again, a negative value, indicating that x equals k is stable. Okay, so this is, again, the analytic criterion applied to a problem we know how to solve. It turns out that oftentimes the analytic criterion is a good backup or sometimes a better way to identify stability of an equilibrium solution of an autonomous equation in the case where maybe the phase diagram is more difficult to understand. Okay, the last part of this video is a discussion of bifurcations, and we'll start bifurcations not a differential equation, but with a discussion of a bifurcation of a quadratic equation or an algebraic equation. So here we'll go ahead and describe solutions of this quadratic equation depending on the parameter h. So if you want to find solutions of a quadratic, you might try using the quadratic formula. So I went ahead and wrote that down here, is the quadratic formula applied to this quadratic, and we can see that solutions are of the form 2 plus or minus the square root of 4 minus h. So we can make the observation that in the case where h is less than 4, there are 2 real solutions. In the case where h is greater than 4, of course, there's a negative under the square root sign, and we have no real solutions. And in the borderline case, when h is equal to 4, there's 1 real solution. This is motivation of a bifurcation. In this particular quadratic formula, the bifurcation occurs at the value h equals 4. Here we can see graphs of those quadratics. In the case where h is 2, 2 real solutions. In the case where h is 6, no real solutions. And the borderline case where h is equal to 4, where there's 1 solution. So again, here we say that h equals 4 is a bifurcation, and you can tell it's the bifurcation point of this quadratic because if you wiggle that quadratic at h equals 4, you either get no solutions or you get 2 solutions, right? So we would say then that h equals 4 is not robust to small perturbations. So similarly, differential equations often contain one or many parameters. So study of bifurcations of those parameters tends to examine changes in the solution structure depending on the interaction of those parameters. So as we'll soon see, sometimes we might get a new solution where we didn't have one before by varying a parameter, or sometimes a solution might change stability by varying a parameter. And we'll identify those both changes in solution structure as bifurcations of a differential equation. So here's an example, an autonomous differential equation, x prime equals x times h minus x squared. And here our main goal is to construct what we'll call a bifurcation diagram that illustrates equilibria and their stability as a function of this parameter. The parameter of the model is equal to h. So we can find equilibria of this equilibrium solutions of this differential equation just like we did before. One is certainly 0, and then of course there might be another one depending on the value of h. So x equals 0 is always a solution, and x equals plus or minus the square root of h is a solution if we can take the square root of h, so namely when h is equal to a positive number. Okay, so we can construct phase diagrams that correspond to those 2 cases also, right? H greater than 0 or h less than 0. It's starting to look like h equals 0 is a bifurcation, and it is. We can construct phase diagram by thinking about the right-hand side f as a function of x. Here x again acts as an independent variable. So the right-hand side is just a cubic, and depending on whether that cubic has 1, 0, or 3, we get the graph on the left with the 3 zeros, one at 0 and the other 2 at plus or minus h. And then if h is a negative number, we get the graph on the right, just the 1, 0 at 0. So we can see here a couple of different interesting things happen. The first is that changing h creates 2 new solutions as h passes through 0. In addition, changing h appears to change the stability of the equilibrium solution at 0 as h passes through 0. We can see that for h positive, in the case where there are 3 equilibrium solutions, plus or minus square root of h appears to be stable, whereas 0 is unstable. However, as h passes through 0 and becomes a negative number, that equilibrium solution at 0 becomes stable. So we can go ahead and represent that change of stability in what we'll call a bifurcation diagram. So here is a summary of the stability information. So x equals 0 is stable when h is less than 0 and unstable when h is greater than 0. And the equilibrium solutions at plus or minus square root of h are stable when h is greater than 0. So plotting those 3 things now in the hx plane gives us what we'll call the bifurcation diagram. So here h is the horizontal axis, and the equilibrium solutions, the values of x, are the vertical axis. And we typically add a solid line for stable equilibrium solutions, we can see that when H is negative, the only equilibrium solution is at 0, and that equilibrium solution is stable. And that when H is a positive number, there are 3 solutions. The one at 0 is unstable, whereas the other 2 are stable at plus or minus the square root of H. Okay, this kind of analysis works on application problems too. So here's an example of logistic growth with harvesting. So suppose that a population P grows logistically with carrying capacity K and is harvested at a constant rate of H per year. So a reasonable model for this logistic growth with harvesting is the logistic portion, dP dt equals Rp times quantity 1 minus P over K, minus the harvesting portion, so a constant H. And here we're going to investigate how this harvesting rate H affects solutions of the system. So we can certainly find equilibria of this system, and finding equilibria ends up being not a whole lot more difficult than it was before. It's just solving a quadratic in P. So here I'll go ahead and write the quadratic out and apply the quadratic formula to it and manipulate that a little bit to come up with P equals K over 2 times the quantity 1 plus or minus the square root of 1 minus 4H over RK. So we can see something similar coming up from our motivating example, namely that there will be a value of H, of capital H, for which we have 2 equilibrium solutions, and similarly a value for which we have no equilibrium solutions. Okay, so that value happens to be when capital H is less than RK over 4, there are 2 equilibria, or when H is greater than RK over 4, there are 0 equilibria, and as you might imagine, changing that value of H ends up corresponding to moving our quadratic up and down the vertical axis. So in the case of 2 equilibria, we can see that one of those is stable while the other is unstable. And in the case of 0 equilibria, it looks like our solutions are always decreasing. I'm going to call those equilibrium solutions in the case where H is less than RK over 4, P sub T is the red one, and P sub C is the blue one. For our stability, again, to summarize, we can see that P of T equals P sub T is unstable when H is less than RK over 4, and then vanishes when H is greater than RK over 4. We see that P of T equals P sub C is stable when H is less than RK over 4, and similarly vanishes when H is greater than RK over 4. So to represent that information in a phase diagram, here we'll go ahead and just graph the equilibrium solutions as a function of this bifurcation parameter H. So you can see H is on the horizontal axis here, and we have some sort of square root type behavior, a positive or negative branch on a square root. And as H passes through this critical value at RK over 4, those solutions come together, and there is no equilibrium solution for H greater than RK over 4. Okay, so that's the bifurcation diagram for this harvesting rate. The interpretation here is that too much harvesting will lead to no stable population, namely extinction. And if you have a reasonable amount of harvesting, the new carrying capacity, P sub C, is a value that's less than the carrying capacity before. And there's sort of a new wrinkle to this model, namely some threshold behavior. I'm calling P sub T threshold behavior. And you can see from the phase diagram that in that case where you have a little bit but not too much harvesting, if you start out with a population that's not above that threshold, it turns out that the harvesting will be too much for things to overcome, and you'll extinguish your population. However, if you start with a population that's above this threshold, your population will tend toward this stable equilibrium value, which again is less than the original carrying capacity of the unfished model, but a carrying capacity nonetheless. Okay, the last part of this discussion is a discussion of non-dimensional scaling. So This may seem distant from our discussion before, but it'll turn out that this discussion of non-dimensional scaling will come back to inform our bifurcation analysis from a moment ago. So overview of non-dimensional scaling, that oftentimes the dimensionless change of variables can be used to relate model parameters. So the strategy here is to rewrite new variables in terms of old characteristic variables and then substitute those in to obtain a new differential equation. So we'll go ahead and have a look at our logistic growth with harvesting model with a change of variables. X equals P over K. So again, K was the carrying capacity of the unfished model, and we'll take tau, the new time variable, to be RT. And if you have a look at the units of both of these variables, of X and of tau, they're dimensionless. That is, they have no units. So the chain rule tells us how to relate x and tau to p and t, and here it is, dx d tau is dx dt times dt d tau. We know how to write dx dt in terms of p and k. We know what dp dt is. dp dt is just a differential equation, and we can write dt d tau is 1 over r. So simplifying that expression, we end up with dx d tau equals x times 1 minus x minus h, where here little h is capital H over rk. So just an algebraic simplification gives us that model. Dx dt looks like a quadratic with a negative term that honestly resembles our original differential equation, which was dp dt equals a quadratic minus some harvesting term. Okay, so as we'll see in a minute, bifurcations of this new model end up being equivalent to bifurcations of our old model. So we can have a look at equilibria of this solution, or of this differential equation. So equilibria of the x equation are values of x for which x times 1 minus x minus h are 0. So just apply the quadratic formula to identify that those are 1 plus or minus 1 minus 4h square rooted, all divided by 2. We can graph the phase diagram, and you might be getting a little bit of deja vu here. You either get 2 equilibrium or 0, depending on whether h is less than 1/4 or h is greater than 1/4. And we can characterize the stability of those equilibrium values by saying that one is unstable and then vanishes as h increases. The other is stable and vanishes as h increases. And the equilibrium solution, the bifurcation diagram as a function of h, looks similar to the one that happened before. Now, it turns out that the value h greater than or less than 1/4, the bifurcation h equals 1/4, is the same as the bifurcation we had before, where the bifurcation we had before was h equals r, capital H equals rk over 4. So here we've been able to sort of combine the different parameters of the model into a single variable, where we can see that increasing capital H has the same effect as either decreasing little r or decreasing capital K. Okay, so this is the example of bifurcation analysis on a scaled differential equation, and we can see how it's a little bit simpler than doing that analysis on the unscaled version. The trade-off in that is the complexity that comes in deriving the scaled version of the differential equation. Okay, so I hope you've enjoyed this video on autonomous differential equations, an analytic criterion for stability, bifurcations of those autonomous differential equations, as well as a scaling argument for autonomous differential equations. That's it for this video, so we'll see you next time. So long.